Hello, dear students. Welcome to the channel and very welcome to this very new playlist in which we are going to discuss about the 8051 microcontroller in detail. So, in our previous playlist, and I'm not talking about the video only, I'm talking about the playlist, we have discussed about 8085 microprocessor family. So if you want to learn about 80885 microprocessor family, you can check out our playlist. The link will be flashing in the description, or it will be flashing on the top right hand side corner of your screen in the I button. So you can simply click on it and move to that video, and you can learn about 8085 microprocessor. And this video is going to discuss about 8051 microcontrollers in detail. So firstly, the difference about microprocessor and microcontroller, that fact that microprocessor is simply a chip and microcontroller is something that has been designed to do a thing repeatedly, right? So microcontroller includes microprocessor in itself sometimes, right? Your washing machines have microcontroller in it. Any other devices, any smart electronic devices that you would be using will have a microcontroller of itself, which will act as the brain of that particular system, will be placed inside that particular instrument or particular gadget. Now talking specifically about 8051 microcontroller. So this is an 8-bit CPU optimized controller which is optimized for the control application specifically. It comes with 4 kilobyte of chip program memory, which would seem very less right now, but keep in mind it is one of the old controllers. So 4 kilobyte used to be a very big thing back in the time when these instruments were invented. Then it has 8-bit program status word and stack pointer. What is program status word? We are going to discuss about it in detail. Stack pointer, it serves the same purpose as it serves in 8085 as well, right? So it's just used to point the stack memory locations. Then 128 bytes on chip data memory it has. Then we have 32 bidirectional and individual addressables input output lines, which are arranged as 4 8-bit pods moving from P0 to P3. That about them we are going to discuss in detail in the pin diagram. We have 16 bit timers and counters, two of them. We have two 16-bit timers or counters. We have a full duplex series serial data transmitter. We have four regular register banks we are having. We have 64 KB program RAM and 64 KB external RAM addressably. So, and we are going to discuss about RAM in detail as well in upcoming classes. Then we have the interrupt structured with two priority levels. We have on-chip oscillator and clock circuits. We have direct bit and byte addressability. We have binary or decimal arithmetic, which allows us to do the math on your controller itself. We have a signaled overflow detection, right? We have signed overflow detection and parity computation, which gives you a hint about what different flags does microcontroller 8051 holds. We have integrated boolean processor of for control applications as well. So it does not only allows you to do the arithmetic operations, but it also allows you to do the boolean operation or boolean expression, deal with boolean expression as well. And then we have the full depth stack for subroutine return linkage and data transfer, as well as the data storage as well, right? Now that we have discussed about the basics of 8051 and its basic applications or basic features, now let's discuss about the architecture of that 8051 microcontroller, right? So what does it contains? So these are the things that 8051 microcontroller contains. I have mentioned them here. As you can see, it contains 8-bit register A and register B. Register A is again same as 8085. It is an accumulator. Then we have ALU. Then we have the 16-bit program counter and 16-bit data pointer. Then we have something that we don't have in 8085, a 8-bit program status word. We have 8-bit stack pointer. We have 128-byte internal RAM and 4 KB of internal ROM. We have 4 8-bit pods, which I just discussed earlier. We have two 16-bit timers and counters, control register, on-chip oscillator. So we are having all these things. And when we collect all of them together in a microcontroller, how does the picture of the microcontroller looks like? So here's a block diagram for you to get a basic understanding of 8051 microcontroller. So you can see the 5-volt supply is given for VCC, VSS has been grounded, and then we are having some other pins coming out as well. Now about 4 ports, you can see the port 0 containing containing the inputs P0 to P07. We have port 1, which is connected to the latch, port 1 latch, which holds the pins P1 to P1.0 to P1.7 or P17. Then port 2, we have port 2 stands for P2 P2.0 to P2.7, and port 3 moves from P3.0 to P3.7 in pins, right? And now interestingly, port 0 and port 2 connects to program address register, and port 1 and port 3 connects with instruction register and data pointer. Now how and why do they connect, that we are going to discuss in architecture and pin diagram in detail. So let's start with the architecture, and first with first thing that we are going to discuss about, what will it be? So it will be the accumulator, right? So here accumulator has been shown with this ACC symbol. So it is accumulator register, and it is an 8-bit register, and it holds the source operand and receives the results of arithmetic operations including addition, subtraction, integer multiplication, division, boolean multiplication, boolean any other boolean manipulation, anything, right? So it serves the almost same purpose. It serves almost the same purpose that it used to serve back in 8085. It also used for the data transfer between 8051 and any external memory as well. As you can see, we have it connected with TMP2, and we have it connected with this bus which is going to the data pointer. So of course it data pointer is going to it is important to connect it with data pointer. How, that we are going to discuss when we will discuss about the data pointer. Then we have the B register. As you can see, B register is right next to A register. This okay, one point that I missed about accumulator is that some functions which are very special functions like rotate function, test function, these functions will always will be only applicable for my accumulator only, right? It will not be available or applicable for any other registers. Now moving to the B register, which you can see right next to the accumulator on the left hand side. So this register is used sometimes with accumulator for multiplication and division operations, and for other instruction it is also treated as scratch pad register, right? Like it won't have any other function other than the location detection where data can be stored, right? Except that we have ALU. You can see ALU, the signal from TMP to goes to ALU or arithmetic logic unit, and ALU is something that performs the arithmetic and logical operation. Not so difficult, is it? Its name gives it away. Its name suggests you that what operation does that do, right? And all these operations will be done on what data? 8-bit data, right? And then it will be able to perform arithmetic operations like addition, subtraction, multiplication, division, logical operations, boolean operations, anything, right? You can give it an AND gate, OR gate. You can give ask him to find the complement of it. So it can do all such things. Plus, one important and underrated tasks that ALU performs is branching different instructions, because it was important to branch the instruction. Without that it can be very confusing, and branching instruction is something that's been done by ALU. Now the interesting thing I'm going to talk about today will be the program status word, or PSW. This program status word, or PSW, is connected here. As you can see, it's connected to ALU. The data is coming from ALU to PSW, and PSW has a double sided arrow which goes from instruction register and DPTR. So what exactly is this PSW? So it's nothing but the same, it is similar to the register that used to hold different pairs, right? So just like there was a separate register for different flags in 8085, we have this program status word in 8051 for different flags, right? So we all know that the flag will be activated by some of the instructions, like in order to address these flags in a more convenient manner, these flags are grouped to form a progress status word, or PSW. Now flag 1 bit register provided to store the result of same instruction. So A flag is a flip flop that indicates some condition produced by execution of an instruction. Like the carry flag, it will be set if there is a carry or a borrow out of MSB of my result. Same ways, the PSW contains math flags which user can use and program them in different way, right? And user can also use them to register selection bits that identify the register bank, and then it can tell you which register bank is in use currently. So how many flags does 8051 has? It has total 4 math flags: carry, auxiliary carry, overflow, and parity. Now I've already told you about the carry flag. Now the auxiliary carry flag will be set whenever there is a carry out of the lower nibble into the higher nibble, or whenever there is a borrow from a higher nibble into the lower nibble. In that situation, auxiliary carry flag will be set. And then we have the overflow flag, which will be set if the arithmetic overflow has occurred, like some significant digit has been some some significant digit has been last because the size of the result exceeded the captaincy of its destination location, right? In such cases the auxiliary flag will sorry in such cases the arithmetic flag will 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 be set. Then we have the parity flag, which will be set when the result has even parity, like even numbers of 1, right? So it's pretty self-explanatory, very easy to understand. Now 8085 also has three general purpose user flag as well, right? And these flags also go from 1 to 0 by the programmer based on his or her desire. And the flags which are used for general purposes are called F0, GF0 and GF1. So the PSW will contain user program flag F0, while GF0 and GF1 flags are stored in the PCON register. We are no need to worry. We are coming to PCON register as well. Now we have the clock and oscillator, right? So where are clock and oscillator, you can see on the bottom right, bottom left side corner. This is the clock and this is the oscillator connected to it. So oscillator circuit that generates the clock pulse so that the internal operation are synchronized is the heart of my microcontroller. The pin XTAL1 and XTAL2 are provided to connect the resonating network comprising the crystal and the capacitor to form an oscillator, and normally quartz crystal is used, right? So capacitors which are used in order to stabilize network, which capacitor we are using, the quartz. So the crystal frequency is the internal clock frequency of my microcontroller only, right? And also by the manufacturer also in 8085 microcontrollers case, the design that run at a maximum speed and maximum frequency will always be ranged between 1 megahertz to 16 megahertz. Then you can see the program counter on the middle right side here. Here this is the program counter you can see, and program counter will perform the same duty as it used to perform in 8085. If you are following those lectures on regular basis, we have discussed about program counter there as well. So basically it is a 16-bit register. It is used to hold the address of a byte in the memory, and it keeps the track of the execution of my program, right? The program selection bytes are fetched from the location in the memory that are addressed by the program counter only, and whenever the power supply is switched on, the program counter will reset to 0 again. So program counter is automatically incremented after fetching a byte from the program memory. And in case of instructions like jump, call, or interrupt, or connect, during such conditions the position of the program counter can change based on the condition. But one more thing, despite all these facts about program counter is still a resistor. So it cannot accessed by the user because it is a special register, and also it does not have any internal address of itself. right? And coming to internal addresses of different memory locations, let's talk about the data pointer. The data pointer is indicated by the letters DPTR just below the program counter here, as you can see. So data pointer is a 16-bit register which is used to hold the address of a byte in the memory. And this data pointer register can be accessed separately as a lower 8 bits and higher 8 bits. So it can use as a 16-bit register or two independent 8-bit registers as well, right? So always remember, data pointer contains how many bit? 16-bit register. Also it serves as a base register in case of indirect jump, instruction handling, lookup tables, and external data transfers as well. And just like program counter, data pointer also does not have a single internal address. DPL and DPH are each assigned on the address, right? Then we have the stack pointer. You can see the stack pointer here, which connects to the DPTR and instruction register. This one is the stack pointer over here. Now the stack is, you all know, it's a reserved area of the memory in the RAM where temporary information can be used, and an 8-bit stack pointer is used to hold the address of the most recent stack entry as well, right? And this location which has the most recent entry is called top of the stack. But first let's talk about the basics. So when the information is written on the on a stack, the operation will be called push, and when the information is read from the stack, then operation will be called pop. So you either push the stack or you pop the stack. And stacks works on the principle of the last in first out, first in last out, right? So the one who came last will move out first. One more thing, that microcontroller always stores the information or data like stacking plates that we saw in 8085 as well. So if we want to remove the first stack plate, then we want to remove all the plates above the first plate, and we have to remove the fourth plate, third plate, second plate, and then finally we will be able to remove the first plate. So this indicates that the first plate pushed onto the stack is the last one to be popped out from the stack, and that is why the operation is called first in first out. Now this stack is implemented with the help of special memory pointer register called as the stack pointer, and it is of 8 bits. Of course, stack pointer holds 8 bits, unlike data pointer. But the stack pointer contents are automatically adjusted to the point to the stack, and new memory location that is currently pointed to the stack pointer is called as top of stack, right? So this is what top of stack was. And when data is used to stare on the stack, the stack pointer increments before the storing data on the stack, and when data is to be retrieved or popped from the stack, then slack pointer stack pointer decrements the point next available byte of the standard data, stored data. Now this stack array can reside anywhere in the chip, right? But its height is limited to the size of the internal RAM only, and the stack can override the data in a register bank as well, right? So bit addressable RAM, uh, scratch pad RAM areas, such places. So normally the stack is placed at a higher location in the internal RAM in order to avoid the conflict with the register or bit and scratched panel in internal RAM as well, right? Internal RAM area as well, right? So that was your stack pointer. One more point, that after a reset the stack pointer is initialized from 07H, right? So the task will be the stack will be beginning at the location, what location, if initialization took place at 07H, then the stack will begin at 08H. Then we have the internal memory that you can see, and also for the proper operation of the computer system, the system should have memory for program code, right? Memory for program code is normal in the RAM and ROM, so that the data can be changed whenever the program is being executed, right? So based on the fact that 8051 has this internal RAM and ROM, and if this memory is insufficient, then addressing mode is externally addressed using suitable circuits, right? Now this about this internal RAM first. So and about the internal memory, this center that you are saying, this is the internal family, or the internal memory of 8051. So it has 128 byte RAM. The internal RAM is organized in three distinct areas: four register banks of 8 bytes each. Then we have the bit addressable areas of 16 byte, and then we have the general purpose RAM area, right? Which you also call sometimes scratch pad areas as well. Except that we have the four register banks of 8 bytes each, and these banks are numbered from 0 to 3, and each bank is made up of 8 registers named R0 to R7. So total 32 bytes, or 32 working registers from address 00 to 1FH are organized as a 4 register bank. Now for selecting the register bank, 2-bit RS0 and RS1 are provided in the program status work, and if any of the register banks are not selected, then the program can use the area from 00H to 1FH as simple scratch pad RAM or general purpose RAM as well, right? Then we have the bit addressable area of 16 byte, and in this area 16 bytes of internal RAM has always been reserved, whose address ranges from 20H to 2FH, and this 16 byte provides us with 128 bit forming addressable bit, and the microcontroller has given address to these bits ranging from 00 to 7FH, right? Hence known these locations used to be known as the bit addressable location. Even now it's used as bit addressable location. Then we have the general purpose area, and as we know, RAM is located in the scratch pad area, and it lies above the bit addressable area that has address from 30H to 70HF, right? So the RAM area can be used as a data RAM, and the memory of this area is byte addressable. So the programmer may declare stack in this area, provide sufficient number of bytes which are available. Then we have the internal RAM. Um, it's not very essential to run the entire area of the internal RAM of microcontroller as a scratch pad, But the microcontroller has the instruction that allows the internal memory locations to be used as the data pointers. And the registers R0 to R7 in the 4 register banks 0 to 4 can be used as the pointer to point the internal RAM as well as the external RAM. So when the registers R0 to R0 to R7 are used to access the external RAM, the microcontroller requires 16-bit address, right? But for 8051, it's an 8-bit microcontroller. This and the size of the address generated will always be 8-bit. Now coming to internal ROM, that 8085 has a separate memory for program and data both, and these memories have a same address ranges. So the internal ROM is used to store the internal program code, self-explanatory. It occupies the address space ranging from 0 to 0 triple FH. Now the program counter can access the program code bytes from 0 to FFFH, and the capacity of internal ROM is from 00 to 0 FFFH. So for address higher than 0 triple FH, the 8085 will automatically fetch the program code byte from an external memory and by connecting the EA, right? Connecting EA pin to ground. So program counter is not bothered of about where the program could when the program could reside, and the programmer decides whether the code resides in the internal memory or external memory or a combination of internal and external memory or not. Speaking of external memory, let's discuss about it as well. So it's used in the case of the failure or temporary maintenance or insufficiency of internal ROM and internal RAM. Two separate extra memory spaces are made available by 16-bit program counter and data pointer as well, and by different control pins from enabling external ROM and RAM chips. If 1 to 8 bytes of the internal RAM is insufficient, then external RAM is accessible by data pointer, right? And in this 8051 family, external RAM of up to 64 KB can be added up in any chip, but the external ROM up to 64 KB can added to only one clip at the time of the purchasing of your controller. So after that we have the input and output ports, except that we also have the special function registers which are placed to the address space immediately above 128 bytes RAMs, and from address 8H to FFH. Now this 8051 microcontroller operations which don't use the internal 128 byte RAM are accessed by the group of the specific internal register, which were used to call the specific functional register. The SFR memory consists of important registers like accumulator, B register, interrupt control register, PSW timer, right? So some of these registers are bit addressable while remaining are byte address, and some of the address like say locations between 8th to FFH are not used at all, and if we try to use them, then these unused locations that are not defined or are empty, then only we may get unpredictable results. And the program counter is not a part of the SFR, but the program counter does not have an internal RAM address as well. After that, we have four total ports, input output ports. Input output circuits of a microcontroller is totally versatile in its own self, and it connects the microcontroller to the external world. So it has total 4 IO input output parts, like say 32 lines, 24 lines. Out of these 32 lines are for one of the two entirely different functions. So although the microcontroller is a 40, but chip it is appearing for will have 64 pins. And as two functions are multiplied in order to decide which function is supported, we need to we need to see we need to see how the circuit is connected, and what software commands are used to program the pins. Then microcontroller has four ports named P0 to P3. All these ports are bidirectional, and each of these 8-bit ports consider of D-type output, latched and output driver, and input buffer. I'm not going to discuss in detail about each and every individual port. And after port 3, what do we have is we have timers and counters. Now the 8051 has two 16-bit timer or counter registers named timer 0, timer 1. Both these registers can be configured independently to operate as a time of an event counter, right? And when used as a timer of the register, will be programmed to count the internal clock pulses. So the internal clock pulses are generated from a constant clock generator, and the count loaded in this registers have constant time. So the register is incremented every machine cycle, and one machine cycle consists of 12 oscillation periods, and so the counting rate will be 1/12 of the oscillation frequency. And again, the counter or the timer registers are delivered into 8-bit register called timer low, and the timer high will be TL0 to TLH. Combinedly forms the 16-bit timer, and TH0 and TH1 from the 60-bit timer. But the counter action is controlled by the bits of the timer node controller, like timer mode controller register, and the timer 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 counter register mode tcon. So that is the t mod and t cons for you. So that is your timers and counters. Then we have the serial data input output. For opportunity between two computer systems, we need to send and receive the data seriously. And then the microcontroller 8085 has a serial data communication circuit, which uses a register in SFR called SBUF to hold the data, and the register SCON controls the data communication. and the register pcon controls the data rates. Now the SBUF register comprised of two registers physically. One of them is write only, and if used to hold the data that is to being transmitted out from the microcontroller via via any pins, while the others other is read only and holds the data that is received from the external source via RxD pin, right? So again it has four modes: shift register, 8-bit UART, 9-bit UART, and last one is also 9-bit UART but with variable band. Earlier it was with fixed band. Then we have the interrupts. I'm not going to detail about the interrupts, but let me give you the glimpse. Whenever the microcontroller is executing a program, as if the user wants service to an input output device, then the external asynchronous input would inform the microcontroller that it should complete the execution of the particular instruction, the and then fetch the new routine that will service the requesting input output devices. And once the input output devices is in service, then the microcontroller resumes the operation, which forms the point whenever it had stopped. So the external asynchronism or an external asynchronous input applies to the microcontroller is termed as an interrupt itself. And that was the architecture of 8051 microcontroller. We will keep today's class till here. I will be seeing you next time. If you have any queries or question, please feel free to mention them in the comment section below. In case of any feedback or any suggestions, you can mention that in the comment section below as well. I will be seeing you next time with the pin diagram or something related to 8051 microcontroller. Till then, thank you very much for listening and goodbye for now.